This section is entitled Verification of Solutions. I'm going to give you a differential equation. There it is. And I'm going to say that that's the solution. And we need to verify it. You double y prime and you add y, and you're supposed to get 0. So the first thing I would do is find y prime. Because I have y, I have to find y prime and then double it. The derivative of e to any power is e to that power times the derivative of that power. That power is negative a half times x. The derivative is negative a half. If I double it, like it tells me to, I'll get negative 1 e to the negative x over 2. You double a half, you get 1. So I have 2y, and I add y, which is e to the negative x over 2. I add both sides. When I add the left side, I get 2y plus 2y prime plus y. On the right side, I get 0. If you add two quantities, that are exactly the same except for their sign, you're going to get 0. Called additive inverses. These two numbers are exactly the same except the sign's different. When you add them, you get 0. You have negative 3x and positive 3x. They're the same except the signs are different. If you add them, you get 0. Oh, I got 0. That's what I was supposed to get. This really was the solution to that differential equation. Let us try another one. dy dt plus 20y supposed to equal, or does equal 24. And that happens when y is 6/5 minus 6 over 5 e to the negative 22. And we need to verify this. I have to find the derivative and 20y's and add them together. And like magic, I'm going to get 24. Well, if y is equal to this, let us calculate y prime. Well, that's a constant, and its derivative is 0. So we have negative 6/5 times the derivative of that. Well, the derivative of e to any power is e to that power times the derivative of the power. A negative times a negative is a positive. Okay, so I know my answer is positive. Ignore all our signs now. 5 into 20 goes 4 times. 6 times 4 is 24. Do not forget that piece. So that's what y prime is. Y prime is 24e to the negative 22. Alright, wonderful. What's 20 times y? What do you get when you multiply by 20? Well, 5 goes into 20 24 times. So 20y will be 6 times 4 minus 20 goes in there. 5 goes into 24 times. And 6 times 4 is still 24 times e to the negative 22. So you get 24 minus 24e to the negative 22. And you add them. The left side, you get this. The right side, we're adding as well. Oh, these two are the same except they differ by signs. So when you add them, you get 0. And please, please, don't forget to add the 24. Oh, it equals this mess equal 24. Yeah. When does it equal 24? When y is equal to that function. That's the solution. You're given derivatives and whatever, and you're asked to find the y function, or an implicit function. We'll talk about that in a little bit. Here's an easy problem. Y double prime plus y is equal to tangent x. And y is negative cosine of x times ln of secant x plus tangent x. So y is a product. I'm actually going to factor out that minus sign. Y is a product. It's this function times that function. So I need y double prime. So I have to find y prime. It's going to be negative the derivative of what's in the blue bracket. It's a product rule inside the bracket. The derivative of the first term, the first factor, is sine x. Sorry, negative sine x. Times the second function. Plus the first function, cosine x, times the derivative of the second function. Now you should really know the derivative of that function is secant x. But if you don't, the derivative of ln of anything, you put the anything in the bottom and a derivative on top. The derivative, that's an addition, but take the derivatives one by one. The derivative of secant x is secant x tan x, plus the derivative of tangent is secant squared. So we have secant x times tan x plus secant squared x in the numerator. If I fact between here and here, they both have a secant x. Secant x times tangent x gives me that piece. Plus secant x times secant x gives me that piece. But what are we doing with that numerator? That's the numerator on the bottom. Now we are dividing it by secant x plus tan x. But this bottom is the same as tan x plus secant x. This cancels out and you just get secant x. So this mess is just secant x. But wait a minute, that's 1. That's exactly 1 because cosine x is cosine x times secant x is 1 over cosine x. So we have cosine x times 1 over cosine x, which is 1. So this whole mess is just the most complicated way to write 1. So now we have that extremely complicated way of writing the number 1. Wonderful. But we don't want or need y prime in this problem. We need y double prime. All right. So I take the derivative of y prime. Negative. The derivative, first function, second function. In fact, I'm going to distribute the minus sign. So this will become plus, and that'll become minus. Okay? The derivative of sine x is cosine x times the second function. Product rule. Plus the first function times the derivative of the second function. Oh, wait a minute. We just took the derivative of that right here. And we got secant x. You want to do it again? Do it again. I'm not going to say a word. I will say this word though. Sine x times secant x is sine x times secant x is 1 over cosine x. So I get sine x times 1, which is sine x, over cosine x. which is tangent x. That's just tangent x. Okay, that is the second derivative. That is the second derivative. And I am going to add on y. I'm going to add on y. Y is negative cosine x ln of secant x plus tangent x. So when I add them, when I add the left side, I'll get y double prime plus y. When I add the right side, it turns out that this and that are exactly the same, except the signs are different. So when I add them, bye-bye. So all that survives is plus tangent x. Look at that. It worked. Y prime plus y really was tangent x. So that's the solution. I know it is. It worked out. Okay, let's raise the difficulty a little bit. Once we rewrite this, everything will come together nicely. 2xy dx plus x squared minus y times dy is equal to 0. A lot of times you'll see differential equations written this way. And they claim that the solution is this. I claim that's the solution. Now, because it's written this way, there's no reason why the answer is that way. That is, this is called an implicit solution. It's a solution, but it doesn't say what y equals or what x equals. Sometimes you can't solve solutions in the form y equals or x equals or t equals. Whenever I say y equals, I mean on the other side there's no y's. If I say x equals, it better not be any x's on the other side. And what I said initially is because this, on the left side, since the differential equation looks different than ones we saw so far, that's not why this answer is implicit. Alright. So we need to work on this left side. We need to have derivatives, y prime, y double prime, y's. Right now we have none of that. Well, we do have a y. What I'm going to do is I'm going to divide each term by dx. So the left one becomes just 2xy. The middle one becomes x squared minus y times dy dx, which is y prime. And 0 divided by dx is 0. So what I know is this original equation and the one right underneath it are exactly the same. They're exactly the same. Now I want to solve for y prime. So I'm going to bring this term to the other side. So I have x squared minus y times y prime is 0 minus 2xy, which is minus 2xy. Okay? All these equations are equivalent. They're the same equation. Now I'm going to divide by x squared minus y. And bingo! I know what y prime is. So this first equation, this very first equation that I wrote down, is the same as this one. So now this looks more familiar. And they're saying the solution to this is that. That's what they're saying. Alright, let's see if they're right. Let's see if they're right. There's a lot of algebra there, but now it's going to become calculus. Just taking the derivative. Now, if you look, the beginning problem never had y equals, excuse me. It says that's the solution. Okay? This here is the solution. Okay, doesn't want to do it. So I'm going to take the derivative and solve for y prime. The first term is a product. It's negative 2x squared times y plus y prime. So when I take the derivative of the first term, the product goes. Take the derivative of the first term is negative 4x times y plus the first term, and instead of adding a negative, I can just subtract, times the derivative of the second factor, the derivative of y prime, plus the derivative of y squared is 2y times y prime. And the derivative of 1 is 0. Now, I want to talk about that. Suppose you have y squared is equal to 3x plus 4. And we want to take the derivative with respect to x. Whether your teacher ever said this or not, it's true. The derivative of 3x is 3 times. Every time you take a derivative, you have d something over d something. It's the derivative of x, and I'm taking things with respect to x. And if I had plus 4y squared, I'll have the derivative, this is 8x. It's in terms of x's, I only see x's there, with respect to x. And of course, this cancels out to 1. At least we can think that, and we'd be right. The derivative of y squared, just like the derivative of x squared, is 2x. The derivative of y squared is 2y times, it's in terms of y, there's only y's there, with respect to x. That's why every time you take a derivative of a y term, you end up with y prime, or dy dx. So we're going to solve for y prime, and we're going to see whether or not y prime equals that. So these two terms have y prime. I'm going to bring this one to the other side. 0 plus 4xy is 4xy. And what remains has y prime, which I can factor out. I have positive 2y, y primes, and I'm taking away 2x squared y primes. I can divide both sides by 2y minus 2x squared, but that's the same as this. I just backed it out to 2. Why did I bother to do that? Because this 2 goes into 4 2 times. This cancels, and I get y prime is equal to 2xy divided by y minus x squared, which is exactly this, because if I multiply the top by negative 1 and the bottom by negative 1, then I multiply by 1. Negative 1 over negative 1 is 1. And multiplying by 1 will never ever change the value. Negative 1 times negative 2xy is negative 2xy. Negative 1 times negative x squared is positive x squared. Negative 1 times y is negative y. And yep, I got the right answer. Let's try another one. That's how you learn differential equations, by working problems. Okay, so before we do the next problem, we just need to review something. If you have an integral of a function of t dt, well, first of all, when you integrate it, you get another function of t. And if you evaluate this from g of x to h of x, then you have to evaluate big F from g to h. That is, you get 8f of h of x minus f of g of x. Like always, first we plug in the upper limit, then the lower limit. Well, this is a function of x. Okay, that's one thing. What I wrote, and that's this. This here is a function of x. If I wanted, because it equals this. It equals this, which is a function of x. So if I wanted to take the derivative, I would take the derivative with respect to x. Taking a derivative of that integral with respect to x. Now, how do you take a derivative of such a function? Well, first, everything pretty much involves f of t. First, you plug that in for t, that is, you get f of h of x, and then you multiply by the derivative of that upper limit, minus, now you plug in g of x for t, and you get f of g of x times the derivative of that lower limit. For example, if you had the integral of t cubed dt, and you're going from 7 to x squared. And you're asked to find the derivative. Now there's two ways of doing this. You can evaluate this integral and then take the derivative of your answer, or you can just do this. First, you want to plug x squared in for t. So you get t cubed, x squared cubed, times the derivative of that limit, the derivative of x squared, minus, now instead of t, I'm going to write and say 7. 7 cubed times the derivative of that limit. The derivative of a constant is 0. So whenever, say, the lower limit is a constant, you're going to get 0. Same for the upper limit. X squared cubed is x to the 6th, times another x is x to the 7th, times 2. So that would be the answer. Again, if you want to take the derivative of a definite integral, first you plug in the upper limit for t, times it by the derivative, minus, then plug in the lower limit for t, and multiply by the derivative of the lower limit. Called the chain rule for integrals. Now, here is a nice looking differential equation, y prime plus 2xy equal to 1. And you're told that the answer for this is y is equal to e to the negative x squared times an integral from 0 to x of e to x squared dt, just one term, plus c1 e to the negative x squared. Now, we claim that this is a solution to the equation on the left. So basically, I need to calculate y prime, and then I need to multiply y, which I have over here. I need to multiply it by 2x. And once I do that, when I add them together, I should get 1. So let's first calculate y prime. Now, the function y, has two terms. This term plus that term. So I'm going to take the derivative of the first term first, plus the derivative of the second term. But the first term is a product. It's this times that. I have to use a product rule. So it's a derivative of e to the negative x squared, which is e to the negative x squared, times the derivative of that exponent. The derivative of negative x squared is negative 2x. So that's what y prime is starting off as, times the second function, integral 0 to x e to the t squared dt, plus, now I keep the first function the same way, e to the negative x squared, times the derivative of this function. So first, the variable is t, so first I plug t in for x, I get e to the x squared times the derivative of x, which is 1, minus, then I plug in 0 for t, but no matter what I get, I'm going to multiply it by the derivative of that constant, which will be 0. I'll get e to the 0 squared times 0. Well, this here is just e to the x squared minus, well, anything times 0 is 0. It's just e to the x squared. So I'll put that, e to the x squared. E to the x squared. So that's the end of the product rule. That is, I just took the derivative of the first term, plus the derivative of the second term. The constant just stays there. The derivative of e to any power is e to that power times the derivative of the power, which is negative 2x. Now the thing is, adding a negative, I can just take away. Instead of adding negative 2x, I can just take away negative 2x. Okay, that's y prime. So I have this and I'm happy. Now I have y, it's right here, that's y. I need to multiply it by 2x. So 2x times y. So first I multiply this by 2x, and I will get 2x e to the negative x squared times this integral stuff dt, plus I multiply this by 2x. There is this, and multiply it by 2x. Now I add them. I add the left side, only I can write a plus. I add the left sides and the right side. When I add the left side, I get y prime plus 2xy. Now when I add the right side, I am adding. Well, I have this piece, and up here, I have the same exact one, except the signs are different. This one is negative, the other one is understood to be positive. When I add them, I get 0. Okay, so that's 0. And I say, oh, look at this. These two, those two are exactly the same, except the signs are different. This is plus, this one's minus. When I add them, and I am adding them, they vanish to 0. All that survived is plus e to the negative x squared times e to the positive x squared. Well, if I'm multiplying and the bases are the same, I add the exponents. Negative x squared and x squared. That second x squared having no sign is understood to be positive. Oh, you mean I'm adding things that are exactly alike except the signs are different? I'm going to get 0. And e to the 0 is 1. That is y prime plus 2xy is equal to this mess, which equals to this, which is 1. So it checked. I wanted to verify that given the y in the top right hand corner, when I took the derivative and I added on 2 times y, I'll get 1, just like it told me to get. So it did work. Try one more. One's a bit messy. Nothing's hard, but it is messy. We have x cubed y triple prime plus 2x squared y double prime minus x y prime plus y, and this is supposed to equal 12x squared. And I want to solve this. That is, I want to get some kind of an equation that doesn't have derivatives. For example, I can say that maybe this is the answer. Or 3y cubed plus 4y squared x minus 7y x to the fifth is equal to 11. That can be the answer. Now, what would it mean for this to be the answer? It means if I took the derivative, if I solve for y prime and y double prime and y triple prime, and I multiply y triple prime by x cubed and y double prime by 2x squared, etc., I would get 12x squared. Notice these answers, possible answers, they don't have derivatives. If you were taking a multiple choice test and you were asked which of the following is the solution to that, and A was xy prime plus 4y equals 7, and B was x ln of y squared square root of xy all to the fifth, and letter C was y prime equals 4x, and letter D was y equals 3y double prime. You should pick D, because the solution should not be a differential equation. I mean, if it can be a differential equation, then this is the answer. This differential equation is valid. Even if it would turn out that xy prime plus 4y equals 7, maybe from this top equation you can actually arrive at that, but it's still wrong. Even if that top equation did imply that y prime was 4x, because y was 2x squared then. The derivative of this is 4x, the derivative of that is y. I'll say that again. The integral of this is that, and the integral of that is y. Or the derivative of y is y prime. The derivative of 2x squared is 4x. But even though these two statements are equivalent, that's not right. You shouldn't have derivatives in your answer. And the last choice y equals 3y double prime that has derivatives. Okay. Now they're going to give us the answer, because this is verification section. In later sections, we're going to learn how to find the solution. But before we can find the solution, we should be able to check to see that it's even right. So that's what we're practicing now. You are told that y is some multiple of x to the negative 1 plus some multiple of x, any multiple, plus some multiple of x, ln of x, plus 4x squared. Now, if this really is the solution, then there's infinitely many solutions. Like y is equal to 2/3 x to the negative 1 plus pi to the e, that's a number, times x plus ln of pi times x ln of x plus 4x squared. These constants can be anything. Now, as the original equation says, or includes, it includes y triple prime, y double prime, y prime, and y. So we need to get all of them. Well, fortunately, I have y. It's the second line. Now I need to compute y prime and multiply it by negative x. So let's find y prime. Bring down the power, get negative c1x, make the new power 1 less, plus any constant times x. The derivative is the constant, plus c3 times the derivative of that. Since it's x times ln of x, when I take the derivative, and use a product law, and do the derivative of the first, which is 1, times the second function. Then I reverse it. That is, I keep the first function the way it is, and I take the derivative of the second function. The derivative of ln of x is 1 over x. 1 times ln of x, plus a number times its reciprocal is 1. That is, I get ln x plus 1. And it's supposed to be multiplied by c. So what I really get is c3 ln of x plus c1, c3 times 1 is c3. So it gets 3c ln of x plus c3 plus the derivative of that, which is 8x. That's y prime. Let's calculate y double prime. You get 2c1 and make the new power 1 less. The derivative of a constant is 0. Plus the derivative of a constant times ln of x is the constant times the derivative of ln of x. The derivative of ln of x is 1 over x. But I'm going to write it that way. This is friendlier for next step when I have to compute the derivative. Okay, the derivative of c sub 3 is 0, plus the derivative of 8x is 8. So that's the second derivative. Now we compute the third derivative. We're going to get negative, use the same color. We're going to get negative 6c1 x to the negative 4 minus c3 x to the minus 2, and then the derivative plus the derivative of 8 is 0. Adding 0, you don't have to bother. So now I have the 4 derivatives. I need to multiply y triple prime by x cubed. So x, use a different color. X, y triple prime. Make that x cubed y triple prime. Need to multiply negative 6c1 x to the negative 4 etc., need to multiply this by x cubed. So I'm going to get negative 6c1 times x cubed. Well, when you add those powers, you get negative 1 minus c3 x to the negative 2 times x cubed. And when you add the 3 power and the negative 2 power, you get 1. So it's negative 6c1 x to the negative 1 minus c3x minus c3x. Okay. Now we need to compute 2x squared times y double prime. 2x squared times y double prime. So here's 2x squared, and here is y double prime. Copying it right from there. 2c1 x to the negative 3, etc. The 2 times the 2 is 4, times the c1, and x squared times x to the negative 3. You add those two exponents and you get negative 1. Now I multiply those two. Get plus 2c3 x. You add the exponents. 2 and negative 1 is 1. You don't have to write the 1. And then you get plus 2 times 8 times x squared. Now, you need to take away x times y prime. You need to compute negative x times y prime. So y prime is whatever it is. It's right above. It's c1x to the negative 2, c2, etc. Just copy it from y prime. And we get negative xy prime is positive c1. And there's an understood 1 in the power. When you add it to the negative 2, you get negative 1. Minus, a negative times a positive is minus c2x. And then minus c3x ln of x. And then minus xc3. And then minus 8x squared. Okay, we're almost done. Now we just have to add on y. And they told us right here what y equals. That was actually given. Y is equal to c1 x to the negative 1 plus c2x plus c3x times ln of x plus 4x squared. When I add the left side, I get this. I get that. When I add the right side, let's see what I get. Turns out that the first column happens to have nothing but cx to the negative 1. The last two have 1. Well, I have one of them. Them are c1x to the negative 1. I add another one. That means I have 2. I add another 4 because I am adding. That gives me 6. Then I take away 6. They're all gone. They're all gone. Now I'm taking away c3x, and I'm taking away another c3x. So I took away 2 of them, and then I add back 2 c3x's. That cancels. I have c2x. I take away 2cx. that cancels. I have C3x ln x plus, that means I have. And then I'm taking away C3x ln of x. Well, that cancels. Looking good. I have 16x squares, and I take away 8x squared. That leaves me with 8x squared. And then I add 4 more, I get 12x squared. Just like I was supposed to. So it checked. It could be a pain in the neck to check it. No argument there. But all you had to do was calculate the 3 derivatives. So let's recap what we did. I was given y. It's the order of this equation is 3. So I calculated y prime. I then calculated y double prime. I then went and I calculated y triple prime. And then, like I said, I took y triple prime and I multiplied it by x cubed. That gave me that equation. Then I took y double prime and I multiplied it by 2x squared. That gave me that equation. And then I took y prime and I multiplied it by negative x. That gave me that equation. And then I just wrote down y and I added them all up together. And the left side was exactly this. It was exactly this on the top. The left side of the equal sign. Exactly that. I didn't have space to put it down there to make believe you see it. And the right side, when I added them, lots of stuff canceled out except those 3. And when you added those, you got 12x squared, just like the problem said. So no matter what C1, C2, and C3 are, it'll work. It'll work. Why? Because, for example, no matter what C1 was, all the terms that had C1 cancel. And no matter what C3 was, those 2 terms and these 2 terms cancel that. Actually, all the terms that had C3 canceled out, including that one there. And then these 2 terms had C2. They canceled out. Now, what I'm getting at is, if you had C3x and you add 2C3x and you take away C3x ln of x, and then you add back C3x ln of x, and then you took away another C3x, this is gonna be 0 no matter what C3 is. That sum is gonna be 0. No matter, this sum is always gonna be 0 because these 3 terms are going to add up to 0. You have negative 8. I'm letting C3 be 8. Negative 8x. And then, hold on. And then I have plus 2 times 8. I have 16x. And then I take away 8x. That's 0. 16 minus 8 is 8, minus another 8. And then I add up those 2. Negative 8x ln of x plus 8x ln of x. That canceled out. Even if x were 81, this is 0. Negative 81, negative 81. This will be 162. 2 times 81. No matter what, the sum will be 0. Doesn't matter what x is. which means we have an infinite number of solutions, which isn't surprising. And the reason it shouldn't be surprising is if you have a constant, when you take the derivative, it's going to become 0. In other words, if you have y double prime plus y prime is equal to 3x, and I tell you that f of x works, some function of x works, that is, it just works. Now, if you add a constant, now just because I'm going to call it g of x. What I know is that before I added the c, y prime will be g prime of x, and y double prime will be g double prime of x. That is, b double prime of x plus g prime of x, I know is 3x. We know this because y equals g of x is a solution. But now, even if I add on the constant, it still is going to work. Why? Because y prime will be the derivative of this. Well, the derivative of g of x is g prime of x plus the derivative of a constant is 0. That is, I'm still getting g of x. And even though there's a constant here, there's no constant here for y prime. So the second derivative is just g double prime. So y double prime is that, y prime is that. When I add them up here, I'm getting 3x. Of course, if you have a y in it, well, we know that, forget the c for a moment, we know that g of x plus g prime double prime plus g prime equals 3x. Problem is that you can add a constant. You can't always have an open variable. There are lots of times you can. The reason you can in this case is y will be g of x plus c plus y prime, double prime, is g double prime of x plus, it does say plus, y prime, that's g prime of x. Well, this is not 3x, it's 3x plus c. This plus that is 3x plus c. Unless c is 0, it's not 3x, so it's not guaranteed to be a solution. For lots of times, we'll have an infinite number of solutions. This completes this section on verifying solutions to differential equations.